Dear students, I would like to give you some introduction to the problem of the basic processes in the vapor. In the last time I have introduced the vapor, I showed you how it's possible to calculate the thermodynamics properties of the vapor. And today I would like to introduce the basic processes, which are very similar as in the ideal gas, but in this case we shouldn't forget that we had practically, or that we have practically two different area, the area of the superheated steam and the area of the saturated mixtures. The problem is that the basic processes, which I have already introduced for the ideal gas, are completely different in the isochoric process, especially in the area of the saturated mixture. So isochoric process, the first one, it's a process which is typical for which is typical that volume, the specific volume remains constant. That means the change of the volume will be zero. This is the same what practically which I have already said in the ideal gas. Now, if you just show below, or I can show you below, these graphs for the PV, TS, and now we can use as well the enthalpy and entropy. This is the last one graphs, and you can see how you can indicate these basic processes. For PV diagram, it's very simple. We can see already that the technical work is just non-zero value, the absolute work is zero, and there is no difference between the area of the superheated steam and the mixture steam. If you look at the TS diagram, now you can see the basic difference. The slope of the line indicates the isochoric process is completely different for the superheated area and for the mixture area. The saturated mixture area, it's just, you can find it in the area between the lines below the critical point. I have already told you in the last time where the saturated mixture area is. Now we can see how the process will be running. That means we start from the point 1 and we finish in point 2. In TS diagram, the surface below this line indicates the amount of the heat. If you just look at the last graphs, you can see very similar process. However, in the enthalpy entropy diagram, again, we can see the critical point, and this line x1 and x2 indicate the quality of the vapor, which will be changing if we perform the isochoric process. If you would like to calculate the isochoric process, that means how you can influence just this quality of the vapor, you can use the formulation which are here. That means we suppose the change of the volume is zero. That means the specific volume for the point 1 and 2 is the same. It doesn't matter if we are talking about the superheated area or in the saturated mixture. And from this definition, you can see here we can calculate the new quality of the vapor x2. Please think about this. Try to sketch uh, yourself to indicate this basic process in the PVTS and in the enthalpy entropy diagrams. The next process is the isochoric process or the isobaric process. And if we are talking still about the isochoric process, excuse me, so we can calculate the heat, and the heat will be calculated using the change of the inertial energy. You can see here that this internal energy U2 and U1 is just the very simple things. That means you will find this value in the table. Please don't forget that you cannot now use the approximation for to express the internal energy, because you cannot use the temperature. If you use the temperature, it will be valid only for the ideal gas and not for the real gas. But I told you that the steam is nothing else as a real gas. It will be very dangerous to use the assumption which we have already used it for the ideal gas. So never use the temperature. Please still working with the internal energy. That means U2, U1, and you will find this value in the tables. In this lecture, I give you as well some scan of the table for the steam, and you will find it in the attachment of this presentation of this lecture. Isobaric process. Now I start the isobaric process. It's very similar as the isochoric process. That means the pressure will be the same. The technical work is zero. The absolute work it's possible to calculate. Now we have to calculate for the superheated area or for the saturated mixture area. The heat can be expressed using the enthalpy, which is the best way. Again, the enthalpy you can find in the table, and just below you can see this process indicates in the three basic diagrams. That means PV diagrams, and the surface below the lines indicate the absolute work. In TS diagram, the same, the surface correspond to the amount of the heat, and in enthalpy entropy diagram, it's a use it just for the calculation. If you know that from this diagram you can find the value of the enthalpy, and if you can express the difference of the enthalpy, you will be able to express directly the amount of the heat. For the superheated vapor, in the specific area, we can calculate the enthalpy using temperature. I want you to do it, but is it possible? Because at the previous presentation, you could see that the paper or the enthalpy depends on the temperature and depends on the uh, CPP, which is the heat capacity for the constant pressure for the superheated vapor. And you can use these tricks to calculate, but only for the superheated area, and you should be sure that you are very far from the line of the condensation. Isothermal process. It's very simple to indicate in the TS diagram. That means temperature will be constant. Is shown how it's possible to calculate the technical and the absolute work. Everybody can see that we use just nothing else as the first law of the thermodynamics. Of course, if the entropy is known, you can use as well the theory of the heat to express the amount of the heat for these changes. In PV diagram, to indicate this change is relatively difficult. You can see that in the area of the saturated mixture, the process is practically not only isobaric, but as well the isothermal. So you can see the very similar line for the PV and TS diagram, practically the same. In the area of the superheated vapor, it's completely different. You have to practically remember this process in order to indicate correctly. In entropy and enthalpy diagram, the line of the isothermal process is a little bit different. So the slope is different. You can see that it cannot be increased so fast, and just you have to again remember how to indicate this process in this area. The last basic process is an isoentropic process. The entropy will be constant. Again, you can see how to calculate the absolute work, technical work. Again, you can use actually the thermodynamics properties like the enthalpy and the internal energy to express this value. Be careful, the same as in the previous processes, there is a difference between the saturated mixture and between the superheated area of the steam. How to indicate a process is depicted here in the PV, TS, and entropy diagram, HC. And you can see that again, you have to maybe remember how the processes can be indicated. Because the entropy is constant, it's very simple to do it in TS diagram. From the TS diagram, we can see it that the amount of the heat will be zero, which corresponds well to the theory, which I have already introduced it for the ideal gas, nothing new. So the isoentropic process is a process defined as adiabatic without heat change. This fact can be used for the calculation. So if you look at the formulation of the work, it's practically derived from the first law of the thermodynamics under assumption that heat will be zero. In HC diagram, enthalpy entropy diagram, it's as well very simple to indicate because the entropy is constant. This is a very important process because just the expansion in the turbine, or which is used for the cycles or the pump, it's just based on the theory that we suppose the adiabatic process is an entropic process, and it can be used for the calculation. So please still keep in mind that this process is defined under conditions that the term that the practically heat will be zero, and you can use it for calculation of the work just if you apply the first law of the thermodynamics. In the PV diagram, it's just this process difficult to indicate. The best way what you can do it is just to remember, but because you will prefer the first law of the thermodynamics, maybe it is not so important just to remember these lines, but I can recommend to try to keep it in mind if it's possible. Now, why we need actually the theory of the vapor and the basic processes? Of course, the very important engines and facility which we needed today, it's just the power plant. It can be the coal power plant, it can be the nuclear power plant, it can be as well the power plant based on the sun and so on, sun energy. So a lot of equipments today which we use it for the energy transfer from the heat to the mechanical work use so-called the Rankine-Clausius cycles. And we can show now how to calculate. You can see here the coal power plant which burn the coal, create the heat. Heat is used to create the vapor, and the vapor goes to steam. In this case, the vapor it's in the superheated area. In the steam, there is an expansion. We know already that this is the adiabatic isoentropic process, which is some kind of the simplification. In the steam turbine, this pressure energy of the steam will be transferred into the mechanical work of the turbine wheel, and it will be used to drive the generator. Generator produce the electricity. Of course, you have to stop this process very close to the line of the condensation, because during the expansion there is a drop of the temperature and the steam start to condensate. The condensation means that you will be no more in the superheated area of the steam, but in the area of the superheated mixture. And you know this is two-phase problems. That means gas and small drops of the steam can be coexisting, and this non-homogeneous gas conditions create as well the big load on the blades of the turbine. And especially at the higher speed of the turbine, in the last state of the turbine, these small drops of the steam can very fast destroy the surface of the blade, lead to the cavitation. In order to prevent this, you stop this expansion, you perform the condensation. That means you change completely the gas or the all gas bubbles in this mixture into the liquid uh, fluid, which is nothing else as a saturated liquid, and you use the pump to increase the pressure and heat once again. And this process will be practically continuing, will be repeating, and we can call this process as a cycle. And the cycle, it's well known under the name Rankine-Clausius cycles. Here you can see once again what I have already said. Please read carefully, decide, and you can understand what has been done actually in each component of the cycle. It makes no sense to speak about this, and please do it yourself. And of course, you need to indicate this process into the TS diagram, which is the best one, because you will be able to observe what can happen with the temperature of the steam, and simultaneously the entropy can inform you about the change of the thermodynamics properties. And because you know that between the TS diagram, the surface indicate the heat, you will be able to see what can happen with the energy. Between the point 2 and 3 with one lines, you practically supply the energy of the heat, which is used to produce the superheated steam. The point 3 one lines to 4 one lines, or if you start for the saturated uh, gas, for the saturated vapor, then it is a line between 3 and 4. You can see that it's blue lines. This indicate nothing else as expansion in the turbine. And I said you have to stop after you reach the condensation line. So the line between the 4 and 1, or for one lines and 1, it's nothing else as a condensation. After condensation, you increase the pressure with pump. It is indicated by point 1 and 2, and the process will be again repeating. Between the 2 and 3 one lines, you supply the energy. Between the 3 and 4, you obtain the energy done by the turbine. And between the point 1 and 2, you have to deliver the energy to increase the pressure of the liquid fluids. Now we could see that we are working with the energy, and we will be able to express how good or how efficient we can transfer the energy. So if we would like to define the thermal efficiency of this whole cycles, we can say this is the work which is produced by the turbine, which we can use it to drive the generator, divided by the total amount of the supply energy, which is in this case mostly the heat. This work, which is done by the turbine, theoretically we should extract uh, by the work which is used for the pump, because in order to pressurize the fluid we need the work as well. But because this portion of the work it's very small comparable to the work produced by turbine, sometimes it's actually neglect. But in this case, we can take into account. And if we insert into this previous definition of the thermal efficiency of the cycle, we can see the thermal efficiency of the Rankine cycle. It's nothing else as a practically ratio between the net work produced by the turbine, that means turbine work extracted by the work needed for the pump, divided by the total supply energy in the form of the heat. In order to calculate, mostly use the facts that the process of the expansion in the turbine is adiabatic. It means the Q will be zero, and if you look at the first law of the thermodynamics, that means the turbine is proportional only to the change of the enthalpy divided multiplied by mass of the steam. They're very similar. You can do it for the pump. Again, in the pump, we suppose the adiabatic isoentropic process, and the amount of the heat which is supplied to create the steam can be expressed very similar. That means we can now say that the work will be zero, and the technical work must be zero, because the furnace which is responsible and heat exchanger inside of the furnace which are responsible to produce the steam, they cannot they cannot deliver, or they cannot do any work. That means the technical work will be zero, and from the first of the thermodynamics, the second form, we know the amount of the heat supply to the steam, it's used only to change these properties. That means it can be expressed as a difference between the enthalpy multiply by amount of the mass, steam mass. And you can now use this formulation to indicate or to determine the thermal efficiency of the cycle. And because we suppose the mass of the steam will be the same, that means practically we cannot change the mass of the steam. The mass plays no more any role, and we can indicate that this thermal efficiency can be defined as a change of the enthalpy. This is the common situation, common way how you can express the Rankine cycle efficiency. And now we can look at the history a bit to imagine what could happen. So please look at these graphs, and it indicates how the thermal efficiency of the steam engines and later the steam turbine cycles was changed during the time. So we start maybe in the first design of the steam engine, which will be in the 17th. That means practically the 17th centuries. And in this time, the Newcomb suggested a steam engine which will be working with the thermal efficiency of 0.5%, which is very, very low. Actually, the big progress was done about the 18th years. James Watt supposed to improve the steam engine, and he reached the 4%, which was more attractive for the coal miners to pump the water. And practically from this time, we start to speak about the useful usage of the coal energy of the heat to change to the mechanical work. That means the steam engines, the area of the steam engines just started. The first power station which was used to produce the electricity, they reached the efficiency about 3%, which was very terrible, but it was before 20 centuries. But how you can see it, the progress of the efficiency of the steam turbine went drastically forwards, and about 1950 the average efficiency was just slightly below 20%. It was not acceptable from the point of today, so the engineers are working to increase the efficiency. And you can see the first point, or the first things what you can do is just to increase the pressure between the saturated pressure, that means pressure of the turbine, and the pressure of the condensation. First, they started 127, they reached 30%, they increased to 169, it could increase the efficiency and so on. So if you increase the pressure difference, you can increase the efficiency. The second point, you can increase the pressure of the steam, how you can see it here. That means the first regenerative cycle with the 538 degrees of Celsius with regenerative cycles could reach at the pressure level 127, the efficiency 30. Nowadays, we are working with the pressure about 250 and about 60 degrees of Celsius, and the efficiency above 40% is common. Of course, this area of the efficiencies, this engine, we can call like the first generation of the simple Rankine cycles. So the next point is just to use the second generation and the third generation. Mostly this is the tricks, and maybe you could hear it about this, that you, for example, change the coal into the gas, that you practically start some process of the gasification. That means you practically create a gas, synthetic gas from the coal, and the gas is first burned in the gas turbine. You just provide the first mechanical work which is possible to use it for the electrical generator, and the waste of the energy in the form of the heat you can after that use for the classical Rankine cycle. This combined cycle enables you to increase significantly efficiency. That means this kind of the power plants can work slightly above 50%. This is called sometimes the second generation. And if you combine with the nature gas, that means you create practically the temperature, you will be able to reach the 60%. This is the typical situation for the case that in which we just try to change completely the heat into the mechanical work. Of course, another point is just to use the tricks that you use this waste energy in the form of the heat for heating of the houses, or to use for the thermal processes. And of course, in this case, you increase the efficiency of the thermal efficiency of the whole engine as well. So this is the history of the progress in the thermal efficiency of the Rankine cycles. You can see the big progress, and we will be speaking later about it, how to do it. And I prepared for you the homework. We can say the homework. and you have to calculate the efficiency of the steam power plants according to the parameters which I give you in the PDF file, and I attach as well some tables of the steam of the superheated steam and the steam in the saturated mixture, and you have to calculate the problem. And please keep in mind the deadline to send me the results on my email in order to know that you could understand this problem. Of course, this presentation it's done very fast. I cannot see your reaction, so please carefully all these pages. Try to understand. If you have any questions, please send me the email. Thank you very much for your attention, and bye bye.